Imagine looking up at the night sky. You see a tapestry of stars, each one a distant sun. You might see the faint, milky glow of our own galaxy, the Milky Way. It is a vast collection of hundreds of billions of stars. It feels immense, almost infinite. But what if I told you that out there, in the deepest, darkest corners of the cosmos, there are objects that can outshine our entire galaxy? These are not stars. They are not galaxies. They are something else entirely. They are quasars, the most brilliant beacons in the known universe. They are so bright, they can be seen from billions of light years away, shining from the very dawn of time. These cosmic lighthouses are profoundly mysterious. When they were first discovered in the 1960s, astronomers were baffled. They appeared as faint star-like points of light, but their signals were unlike anything seen before. The name quasar is short for quasi-stellar radio source, which means star-like thing that gives off radio waves. It's a name that captures the initial confusion. How could something so small, so seemingly insignificant, generate such an incredible amount of energy? How could it shine with the light of 1 trillion suns? The answer, we now believe, lies with another of the universe's great enigmas, the black hole. The connection between quasars and black holes is one of the most fascinating stories in modern astronomy. It is a tale of creation born from ultimate destruction. It links the darkest objects in the universe with the brightest. On one hand, you have a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. It is the very definition of darkness. On the other hand, you have a quasar, an object so luminous it defies imagination. It seems like a paradox, a cosmic contradiction. How can absolute darkness be the engine for the most brilliant light? This is the puzzle we are going to explore. We will journey to the hearts of distant galaxies, back to a time when the universe was young. We will witness the epic interplay of matter and gravity on a scale that is almost impossible to comprehend. The story of quasars is not just about bright lights in the sky. It is a story about the fundamental forces that shape our universe. It's about the life cycle of galaxies, the growth of cosmic structures, and the very history of everything we see around us. It is a story that begins with a fall into darkness and ends with a burst of unimaginable light. So, what is a black hole? The idea itself is startling. It is a place where the laws of physics as we know them seem to break down. It's what happens when a huge amount of matter is squeezed into an impossibly small space. The resulting gravitational pull is so immense that it creates a one-way door in the universe. Once you cross its boundary, the point of no return known as the event horizon, there is no coming back. You are pulled towards a central point of infinite density, a singularity. It is the ultimate abyss, a cosmic trap from which nothing escapes. There are different kinds of black holes. Some are relatively small, perhaps just a few times the mass of our sun. These stellar mass black holes are formed from the collapse of giant stars at the end of their lives. But the black holes that power quasars are a different breed altogether. They are monsters. We call them supermassive black holes, and the name is an understatement. They can have the mass of millions or even billions of suns. We now believe that one of these giants lurks at the center of nearly every large galaxy in the universe, including our own Milky Way. Our own galaxy's supermassive black hole is called Sagittarius A. It has a mass of about 4 million suns. It is a relatively quiet giant, slumbering at the galactic core. But in other, more distant galaxies, these behemoths are not so peaceful. They are active and they are hungry. They are surrounded by vast clouds of gas and dust, and even entire stars, all caught in their powerful gravitational grip. This material doesn't just fall straight in. Instead, it is pulled into a swirling, chaotic dance around the black hole, a cosmic whirlpool of epic proportions. This is where our story takes a dramatic turn. The existence of these supermassive black holes was once just a theory. Now, thanks to incredible technology, we have seen their shadows. The Event Horizon Telescope collaboration captured an image of the black hole at the center of the M87 galaxy, a giant with a mass of 6.5 billion suns. Seeing this void, this dark silhouette against a backdrop of glowing gas, was a landmark moment for science. It confirmed that these monsters are real, and it provided a crucial clue to understanding the incredible power of quasars. Here we arrive at the central paradox. If nothing can escape a black hole, how can it be responsible for the brightest objects in the universe? The answer is that the light does not come from inside the black hole. It comes from just outside it. The energy is released from the matter that is on its final desperate journey towards the event horizon. This matter, a collection of gas, dust, and shredded stars, does not simply plunge into the abyss. Instead, it forms a vast, flat, rotating structure around the black hole. This is called an accretion disk, and it is the engine of the quasar. Imagine water swirling down a drain. It spins faster and faster as it gets closer to the center. The same thing happens in an accretion disk, but on a mind-boggling scale. The immense gravity of the supermassive black hole accelerates the material to incredible speeds, close to the speed of light. As the gas and dust particles orbit at these velocities, they rub against each other. This creates an enormous amount of friction. And friction, as we know, generates heat. In the extreme environment of an accretion disk, the friction is so intense that the material heats up to millions of degrees. When matter gets that hot, it glows. It doesn't just glow like a red-hot poker. It shines with an intensity that is difficult to put into words. The accretion disk becomes a cauldron of superheated plasma, radiating vast amounts of energy across the entire electromagnetic spectrum, from radio waves to X-rays. It is this light, this phenomenal blast of energy from the tortured matter in the accretion disk, that we see as a quasar. The black hole acts as the gravitational engine, but it is the accretion disk that is the source of the light. It's a cosmic power generator of unparalleled efficiency. This process is astonishingly effective at converting mass into energy. Nuclear fusion, the process that powers our sun, converts about 0.7% of mass into energy. The process of accretion around a black hole can be more than 10 times more efficient, converting 10% or even more of the mass of the infalling material directly into radiation. That is why a quasar, powered by a region of space no larger than our solar system, can release more energy than all the hundreds of billions of stars in its host galaxy combined. It is a testament to the supreme power of gravity, turning the darkness of a black hole into the universe's most brilliant beacon. For millions, perhaps even billions of years, a supermassive black hole can lie dormant at the center of its galaxy. It is a sleeping giant. The vast majority of the stars in the galaxy orbit it from a safe distance, unaware of the monster lurking in their midst. The immediate vicinity of the black hole has been swept clean of gas and dust. It only receives a trickle of matter, perhaps a small stray gas cloud or an unlucky star that wanders too close. In this quiet state, there is no brilliant accretion disk, no dazzling quasar. The galactic core is dark, but the universe is a dynamic, ever-changing place. Galaxies are not isolated islands. They interact, they collide, and they merge. Imagine two large spiral galaxies on a collision course. Over millions of years, their gravitational fields pull them together in a slow, majestic, and incredibly violent dance. Their spiral arms are torn apart, and vast streamers of stars and gas are thrown out into intergalactic space. The collision funnels enormous quantities of gas and dust from both galaxies towards their combined center. This is the moment of awakening. A flood of fresh fuel is suddenly delivered to the doorstep of the sleeping giant. This sudden influx of matter is the trigger. The supermassive black hole, which had been fasting for eons, suddenly finds itself surrounded by a feast of cosmic proportions. The material, carrying the angular momentum from its galactic journey, cannot fall straight in. It begins to pile up, forming the vast, swirling accretion disk we have discussed. The disk grows larger and denser as more and more material arrives from the galactic merger. The sleeping giant is no longer sleeping. It has been awoken by a cosmic cataclysm, and it is beginning to feed with a voracious appetite that will shake the very foundations of its host galaxy. The stage is now set. All the components are in place: a supermassive engine, a vast reservoir of fuel, and the powerful physics of accretion ready to be unleashed. The birth of a quasar is imminent. As the accretion disk forms and grows denser, the friction within it builds to an unimaginable crescendo. The inner regions of the disk, where gas spirals towards the event horizon at nearly the speed of light, become a crucible of extreme physics. The temperature begins to skyrocket, climbing from thousands to millions of degrees. The atoms in the gas are torn apart, stripped of their electrons, forming a seething, glowing plasma. This is the moment of ignition. The accretion disk ceases to be a dark whirlpool of gas and dust and bursts into brilliant, incandescent light. A new star has not been born. A cosmic furnace has been lit. This is the birth of the quasar. The light generated by the superheated plasma is so intense that it can be seen from across the observable universe. It is a beacon that announces the awakening of the central black hole. The energy released is staggering, dwarfing the combined light of all the billions of stars in the host galaxy. A region of space no larger than our own solar system suddenly begins to radiate with the power of 1 trillion suns. From our distant vantage point on Earth, billions of years later, this incredible burst of energy appears as a single star-like point of light, a quasi-stellar object. The light from the newborn quasar is not just bright, it is a violent torrent of radiation that blasts outwards from the galactic center. This outpouring of energy has a profound effect on its surroundings. It pushes back against the very gas that is trying to fall into the black hole. This creates a complex feedback loop. The quasar's brightness is regulated by its own fuel supply. If it shines too brightly, it can heat up and blow away the surrounding gas, temporarily starving itself. This can cause the quasar to flicker and vary in brightness over time, a behavior we can observe in distant quasars. The quasar is now fully active, a self-sustaining engine of incredible power. It will continue to shine as long as there is a steady supply of fuel falling into the accretion disk. This active phase can last for millions or even tens of millions of years, a brief but spectacular chapter in the long life of a galaxy. During this time, the supermassive black hole will grow significantly in mass, consuming solar masses of material every year. The quasar is not just a light show, it is the visible manifestation of a black hole's primary growth phase, a cosmic rite of passage for the galaxy itself. As if an accretion disk shining with the light of 1 trillion suns wasn't spectacular enough, some quasars produce an even more astonishing phenomenon, colossal jets of matter and energy. These jets are fired out from the immediate vicinity of the black hole, perpendicular to the accretion disk. They travel at speeds incredibly close to the speed of light, 99.9% of it or even faster. These are not gentle streams. They are focused, violent outflows that can travel for immense distances, punching right through the host galaxy and extending for millions of light years into the vast emptiness of intergalactic space. They are among the largest single structures in the entire universe. The exact mechanism that launches these jets is still one of the great puzzles in astrophysics, but it is undoubtedly linked to the extreme environment right at the edge of the black hole. The leading theories involve the powerful magnetic fields that are generated within the turbulent accretion disk. As the disk spins, it twists and amplifies these magnetic fields into colossal spiraling towers of magnetic energy. These tightly wound magnetic fields can then act like a cosmic cannon, grabbing charged particles from the inner disk and flinging them outwards along the black hole's axis of rotation, where there is less resistance. Another theory, known as the Blandford-Zernajek process, suggests the energy for the jets comes from the rotation of the black hole itself. A spinning black hole drags the very fabric of space-time around with it. The powerful magnetic fields from the accretion disk can tap into this rotational energy, effectively extracting power from the black hole and using it to accelerate the particles in the jet. In this scenario, the black hole is not just a passive gravitational well, but an active participant, a spinning dynamo that powers these incredible outflows. It is a stunning idea that we can extract energy from the black hole's spin. These jets are powerful emitters of radio waves, which is how many quasars were first discovered. When we look at the sky with radio telescopes, these jets appear as two giant luminous lobes on either side of the host galaxy. They are created as the jet material, traveling at near-light speed, slams into the sparse gas that exists between galaxies, creating immense shock waves that cause the particles to glow. The existence of these jets adds another layer of awe to the quasar phenomenon. They show that the black hole engine doesn't just consume matter, it can also expel it with unimaginable force across cosmic distances. Once ignited, a quasar becomes the most luminous, persistent object in the cosmos. Its light begins a journey that will span billions of years and cross billions of light years of expanding space. This is why quasars are so important to astronomy. They act as cosmic lighthouses, shining from the farthest reaches of the universe. Because the speed of light is finite, looking at a distant quasar is like looking back in time. The light from the most distant quasars we have discovered has been traveling towards us for over 13 billion years. Given that the universe itself is about 13.8 billion years old, we are seeing this quasar as it existed when the universe was a mere infant, only about 670 million years old. This is an astonishing window into the past. We are witnessing the light from one of the very first massive objects to form after the Big Bang. It is the closest thing we have to a time machine, allowing us to see the cosmic dawn directly. This is why quasars are so invaluable to our understanding of cosmic history. They provide direct evidence of what the universe was like in its youth. The sheer power of a quasar is what makes this possible. An ordinary galaxy made of billions of stars is too faint to be seen in detail at these extreme distances. But a quasar, powered by its central engine, can be hundreds or even thousands of times brighter than its entire host galaxy. This allows our telescopes to pick it out, a single bright point of light from the cosmic dawn. Every quasar we find is a probe, a pinprick of light that illuminates the dark ages of the early universe, giving us a precious glimpse into a time that would otherwise be completely invisible to us. The brightness of a quasar is not just a curiosity, it is a tool. As the light from the quasar travels towards us, it passes through vast clouds of intergalactic gas, the raw material from which galaxies had yet to form. The atoms in these clouds absorb specific frequencies of the quasar's light, leaving a faint imprint on its spectrum. By analyzing this spectrum, we can read the story of the intervening space. We can measure the composition, temperature, and density of the gas in the young universe. The quasar acts like a cosmic X-ray, backlighting the invisible structures of the cosmic web. When we look out into the universe, we see that quasars were much more common in the distant past than they are today. The peak era of quasar activity seems to have been when the universe was between 2 and 4 billion years old. In the nearby universe, active, luminous quasars are quite rare. Our own Milky Way's black hole is sleeping. The giant black hole in our neighbor, the Andromeda galaxy, is also quiet. This raises an obvious question: where have all the quasars gone? Why were they so common in the past but so rare now? The answer lies in their fuel supply. A quasar needs a constant, massive inflow of gas and dust to power its brilliant light show. In the early universe, galaxies were still forming. They were smaller, messier, and much richer in gas than galaxies are today. The young universe was a cosmic buffet for hungry black holes. Over the next several billion years, the universe began to settle down. Galaxies grew larger and more stable. The readily available gas in their centers was either consumed by the black hole, blown away by quasar feedback, or used up in a burst of star formation. The supermassive black holes, having grown to their immense sizes, entered a state of hibernation, a quiet slumber from which they are only occasionally stirred. This means that the quasar phase is a relatively brief, youthful period in the life of a typical large galaxy. The giants are still there. The supermassive black holes still lurk at the hearts of nearly all massive galaxies. They are just dormant. They are sleeping dragons, waiting for a new meal. We have journeyed across billions of light years and billions of years into the past. We've stared into the abyss of a black hole, the ultimate darkness, and from the edge of that darkness, we've witnessed the birth of the most brilliant light in the universe, the quasar. The story of black holes and quasars is, honestly, one of the most profound in all of science. It's a story of beautiful, violent paradoxes. It's where creation is born from destruction, where light erupts from the brink of eternal darkness, and where the smallest regions of space can dictate the fate of the largest structures we know, the galaxies. The black hole is the engine, but the quasar is the roar. It's a testament to the awesome power of gravity, a force capable of converting matter into energy with an efficiency that, honestly, dwarfs even the heart of a star. So when we look up at the night sky, we should remember this incredible story. Among the familiar, gentle twinkle of the stars lies the evidence of these cosmic monsters. The supermassive black hole at the center of our own Milky Way is quiet now, a sleeping giant. But the legacy of its more active cousins is written across the entire history of the cosmos. The light from the most distant quasars is more than just beautiful. It's honestly a priceless artifact. It's a fossil, a relic from the cosmic dawn, carrying information from a time when the universe was young and chaotic. The journey doesn't end here. Every new discovery, every new image deepens our appreciation for the cosmos. They inspire a sense of wonder, a feeling of being part of something immeasurably vast and magnificent. They remind us that there's always more to explore, more to understand, and more to be amazed by. Our understanding is a small island in a vast ocean of mystery, but it's an island that is growing every day.